All right. Welcome to Colossus Mathematics class. Don't forget to subscribe, like, and share this video. In today's class, we'll be talking about electric flux, Gauss Law, and its application. So first, what is electric flux? If you look at our definition here, we say that before I read the other definition, the first thing I want you to note is this definition that says that what electric flux is the measure of of number of field line passing through the surface. Electric flux is the measure of the number of field line passing through the surface S. Now then we now say again, when you now come to this definition here, the definition says that it says that the electric flux passing through any total surface, through any closed surface rather, which is also known as the Gaussian surface, is equal to the total charge enclosed by the total charge enclosed by the surface. Let me read that again. It says the electric flux passing through any closed surface, or you can say that the electric flux passing through any Gaussian surface is equal to the total charge enclosed by the surface. And electric flux is denoted by this sign, which is called phi. I get what I'm saying, and it's given by EA cos theta. EA cos EA cos theta. Are you seeing that now? So the formula is EA cos theta. So let me write my theta clearly. Now, if you look at this our diagram, this is the angle. Are you seeing that now? This is the angle formed. Now you can see from here, this is an example of electric flux. These are the electric field line. These lines that go like this dotted line are the electric field line. And if you know, one of the property of electric field line is that it does not end. Are you seeing that now? It is continuous, and also that it does not touch each other. Are you seeing that now? It does not touch each other. And you can see that the area, this is the area here. Area is this particular line, and it is it is perpendicular to the electric field. Are you seeing that now? It is perpendicular, that is, an angle is formed. Are you seeing that now? That is what we mean by perpendicularity. Now, so what are some of the things you should know about electric flux? Number one is that electric flux is a scalar. Are you seeing that now? Is a scalar, and its unit is Newton meter per seconds per coulombs. How do we get that? You know, electric field is Newton meter. Electric field. You know, this E is electric field. Are you seeing that now? E is electric field. So this is N over over coulomb. Are you seeing that now? And area is meter square. So if you multiply that together, you will have Newton meter square per coulomb. Are you seeing that? That's how we have the unit there. And then I already said it that phi represent the number of field line, and that's the electric flux. Are you seeing that now? So we said for the enclosed surface, the area vector points outward. The area vector it points outward. That's how you can see there. You can see the area here. You can see the area here is pointing outward. Are you seeing that now? So that is what we are trying to say there. All right. So now, if you look at the other thing, we said electric flux is at minimum when theta is equal to 90 degree. Electric flux is at minimum when theta is equal to 90 degree. That is, you can also say that electric flux is perpendicular to the normal. What do we mean by perpendicular? When something is perpendicular, it means it means an angle 90 is formed. Are you seeing that now? It means an angle 90 is formed. That's what you can see there, this sign. Are you seeing that? This is the angle 90. So if theta is equal to 90, that means that we have E. Are you seeing what we are having now? E cos E cos 90. Are you seeing that now? E cos 90, and cos 90 is is 0. So that's how we now have EA into bracket 0. And if you multiply that, you will have 0. Are you seeing that now? So that is how we say that what? It is at minimum. Are you seeing that now? It is at minimum when theta is equal to what? 90 degree. Another thing is, now when is it at maximum? It is at maximum when theta is equal to what? 0. That means when the electric field, look at the electric field, when it is what? When it is parallel to the what? To the normal. Are you seeing that now? When it is parallel to the normal, that means no angle is formed. No angle is what? Is formed. Are you seeing that now? That means theta is equal to what? 0. And if theta is equal to 0, what do we have there? We are going to have what? EA cos what? EA cos 0. Are you seeing that now? And cos 0 is what? Is 1. So that will give us EA. Sorry, that will give us EA into what? Into 1. And that will give us what? E multiplied by what? A. So that is why we can say that our what? Our electric flux is given by what? EA. Are you seeing that now? So this is like a general formula for electric flux. Are you seeing that? EA. Are you seeing that now? Phi is equal to what? EA. Where your E is what? Electric field. E is the what? Electric field. E is electric field, and then A is what? Is area, cross-sectional area. A is what? Cross-sectional area. Now you can see that we say that E is electric field. Now that E, it varies. Are you seeing that now? That E does what? It varies depending on the what? On the particular field you are working on. It depends on what you are working on, and that's what will now bring us to this our next formula, which is what? Application of Gauss law. Now if you look at the application of what? Of Gauss law, you will see something there, something important. We say that what? There are various applications of Gauss law which we will look into now. Before we learn about the Gauss law, let us see how we can apply the law. That means we must choose the Gaussian surface such that the evaluation of the electric field becomes easy. Are you seeing that now? That means your E. So for example, if you want to use EA, depending on the what? On the type of what? Of question you have, that will determine the type of E, your electric field. So the number one here is we have what? Electric field due to what? Infinite what? Infinite wire or infinite wire. Now what does the formula say? That's what? E equal to what? Lambda. E equal to what? Lambda all over what? This is lambda. This sign is what we call lambda. It is called lambda. Are you seeing that now? So lambda equals to what? It is given by what? E equals to what? Lambda all over what? 2 pi epsilon naught r. So what is your lambda? Your lambda is what? Is the linear charge density. Lambda is what? Linear charge density. And then what's it called? Lambda is a constant. You know lambda is a constant, 3.142. Then epsilon naught is also a constant, which is what? 8.85 times 10 power minus 12 Newton meter square per watt per coulombs. Are you seeing that now? And your R is your what? Your radius. Then we have the second application, which is electric field near a plane sheet. Electric field near a plane sheet. Now what does that say? That one is saying that what? The formula will be what? E equals to what? Rho over 2 epsilon naught. Rho, this is rho. Are you seeing that now? This sign is called rho. This sign here is called rho. Are you seeing that now? This is called rho. So rho over what? 2 epsilon naught. So what does rho means there? Rho means surface change. Are you seeing that now? Rho means surface change density. Surface what? Surface change density. Don't forget, we say lambda means what? Linear charge density. Rho means what? Surface charge density. Lambda linear, rho surface. Are you seeing that now? Then we have another one, number 3. We have number 3 that says electric field between two parallel plates. That's what? E equal to what? Rho over what? Epsilon naught. You already know that your rho is what? Surface charge density, and you know that your epsilon naught is what? a constant, which is 8.85 times 10 to the power minus 12. Don't worry, we are going to see example where we are going to apply all these things. All right, so we have the fourth one, which is electric field outside a thin spherical area. Electric field outside a thin spherical shell. A thin spherical shell. That's what E equals to what? KQ over what? Over R square, our normal electric field. All right, and then we have electric field inside a thin spherical shell. You can see that this number 4 is what? Outside a thin spherical shell. This one is what? Inside a thin spherical shell, and that's what? Phi equals to what? Q over epsilon naught. You already know your Q is the what? Is the quantity of charge. All right, so this is just an introductory video. This is an introductory video. So in the next video, I'm going to be doing examples. All right, I'm going to be showing you examples on how you can apply these laws. All right, I'm going to be showing you how you can apply these laws. Don't forget, these are the different E's that you can use. All these are the different E's that you can do what? You can use. Isn't that now? They are the different E's that you can what? You can use depending on what you have, as you'll be seeing in the next video. So make sure you subscribe, like, and share this video. And if you need a private personal class for any courses like mathematics, physics, and any science course, do well to reach out to me by sending a WhatsApp message to this number 07052609233. So that is my direct WhatsApp number. Send a message to the number and I will be there to answer you immediately. All right, so the number again is 07052609233. all right, so don't forget to subscribe, like, and share this video. Turn on the notification bell so that you can see the next video once it is being uploaded. Thank you very much and do have a great day. All right.